Welcome to the last class of this course. In the previous class, what we have observed that instantaneous power in a balanced three-phase system is constant. Due to this reason, three-phase system are preferred to generate and distribute the power. In today's class, I am going to compare the power loss in one phase as well as three phase system, and it is possible to show that in three phase system the amount of wire requirement is lesser than the one phase system, and in order to establish this I have to assume something. So let us see the comparison between the one phase and three phase systems. So I have drawn the one phase system and I have also drawn the three phase system, and here you can see that I am assuming that whatever wire I have used in one phase connection as well as three phase connection, both wire are of the same material, and suppose that one can use copper which has same resistivity, same length, and whatever load I have assumed that is resistive. So whenever if I have load is resistive, then power factor is the unity, and what is our another assumption that line voltage, whatever line voltage that is denoted by here in this particular diagram, you can see that line voltage I have denoted VL. Here also line voltage between any two line, that is VL, and I am assuming that same power is absorbed by this particular resistive source. So let us first write the all assumption. So here I am going to write the assumption. So let us make some space to write the assumption. So basically what I am going to assume that the the line voltage VL and power absorbed PL, because I have to do comparison, are the same in one phase as well as three phase. So basically I am talking about the assumption. So in order to do the mathematical comparison, first I have to make several assumptions. So this is the first assumption. After that, now I am going to talk about, so I am basically going to do several assumptions, and here this is my second assumption. So second assumption is that the both the wires are of same material, and whenever we are talking about the material, then obviously resistivity of the wire is going to involve. So basically I am assuming that some wire, suppose most of time people are using copper wire, so due to that reason I have taken here copper with resistivity, and that resistivity is rho. After that, third assumption is that the length of wire is same, so length of wire, and length of wire I have represented by L, so length of wire L is same. And after that I have another next assumption in order to do the comparison. So I am assuming that that is the our fourth assumption, that loads are resistive, and whenever we are talking about the resistive load means I have unity power factor. So under these four assumptions, now I am going to first write the some kind of mathematical analysis for one phase system, and after that I am going to do the same analysis for three phase system. So here you can see that in this one phase system I have used two wires of length L to connect one phase source to the load. So what I am seen here, what we have seen here, for the two wire single phase system, IL, if you calculate IL in the above figure, since voltage difference is VL and I know the power PL, so I can write the VL, because I am assuming that whatever power loss in both is same, and I am assuming that power is PL. So let us now talk about the total power loss, because I have identified the current. So after identifying the current, I am able to talk about the power loss in the two wire, and this is this can be easily calculated, and one can calculate that power loss like this. I am denoting power loss by P loss, and P loss is IL square into R in one rod, but I have two rods, so I have multiplied by 2. So basically 2 R, and I know the IL, that is PL square by VL square. Because I am assuming that PL and VL both are same, so due to that reason I have expression in form of PL and IL. So after identifying the P loss, means power loss in two wire system, one phase two wire system. Now let us come for the three wire system, because here three wires are involved, or three wire three phase system. So this is three wire three phase system. Now I am going to do the same kind of calculation for the three wire three phase system. So again, here you can see that voltage is the same, and after that power, here whatever load here sitting, that is resistive and has unit power factor, meaning of resistive load. And it is possible to show that line current, that is equal to magnitude of IA equal to magnitude of IB, and that is magnitude of IC, and that is equal to the PL by root 3 VL. And why we are writing that? Because in the previous class we have calculated the average power, and average power is root 3 VL into IL. Due to that reason I have written this kind of expression. Now let us talk about the power loss. So the power loss in the three wire is, I am denoting that by a P dash loss. So that is 3 IL dash square, because current I have assumed like this, into R dash. R dash is the resistance. Now you can see here that I am also able to write IL from the above expression like PL square by 3 VL square. So basically now I have R dash PL square by VL square, and since I know that PL in both cases is equal, and also I know the IL VL is equal in the both case, so same line voltage. Due to that reason I can able to write the loss in the one phase by loss in the three phase wire, that can be written like this, 2R by R dash. So that is just by dividing the two power loss equation. Let us again recheck it. You can see here that power loss is given like this, that is 2R PL square VL square, and here basically in this expression I have again done the calculation of power loss in the three phase wire, and at that time, that is r dash pl square by vl square. So I have just divided p loss by p dash loss, and after that we are able to get this kind of expression. Now I am going to see the expression of r and r dash. So we know that everyone means this we are actually knowing from the 10 plus 2 onward, that resistance R is rho L by pi r square. Similarly, for R dash, I can again able to write like this, rho L by pi r dash square, and where R and R dash are the radius of wires, and due to this reason I am able to talk the following: the power loss in one phase by power loss in three phase, that is 2 r dash square by r square. Now if we assume that same power loss if I tolerate in one phase and three phase, then I have following expression. So let us write the further part of analysis, because we are going to compare the material. So somehow lastly I have to talk in terms of the material, and here material involved is wire. So after deriving this expression of the power loss in terms of the radii, now I have to go for the further analysis. So if the same power loss is tolerated, so is tolerated in both system. So if we are assuming that power loss in first one and second one both are same, then I can easily write that r square is 2r dash. Then only I can assume that power loss in the one phase as well as three phase wire are the same. Now by using this particular relation, I am going to see the material requirement. So the ratio of material required is determined by the number of wires and their volumes, and so I am able to write the following thing, that material for one phase by, I am going to compare the material requirement. So that is material for 3 phase, and that is 2 into pi r square L, and here I have 3 into pi r dash square L. And if you see this ratio, then this ratio is nothing but that can be denoted like this. So finally, from the above relation, where we have established the relation between r and r dash, from there I can further write that 2 by 3 multiplied by 2, that is nothing but 1.333. So, and I have used, because I know, let us, for clarity, right, since I have already derived r square equal to 2r dash. Due to that reason, I am writing like this. And basically, what is interpretation of this particular derivation in terms of material? This derivation shows that the single phase system uses 33% more material than the three-phase system, or in another way, the three-phase system uses only 75% of the material used in the equivalent single-phase system. So, because if I want to deliver the same voltage, and if I want to maintain same power, and if I am willing to maintain the voltage, we are able to see this kind of relation. So in other words, here in this particular analysis shows that less material is needed to deliver the same power with a three-phase system than at it required for the single phase system. So let us just write this remark, because this is very important, and due to that reason people are prefer the three phase power generation as well as transmission. So let us write the remark, and this is the second advantage basically. So first advantage, that instantaneous power is constant, and second advantage, that less material is needed to deliver the same power with a three-phase system. I am representing three-phase system like this. Then is required for a one-phase system. So this is the one of the important remark, and with this remark I am going to close this course. So let us try to see the summary of this course. So we have started this course with the definition of the system, or Or finally, what we have found that how to define circuits and network, what is difference between circuits and networks. And after that, we have seen the development, means parallel development of mathematics, and how basically mathematics helps us to analyze any physical system. So we have actually talk about the axioms, we have talked about the theorems, lemma, everything, and I have already told you that how basically mathematical experiment is different than the physical experiment. And after that, we talk about some kind of fundamental laws, that is Kirchhoff's law, Kirchhoff's voltage and law, and Kirchhoff's current law. After that, we have talked about the more theorems, and that is somehow related to the nodal analysis, mesh analysis, superposition theorem, linearity, and after that we have come to the Thevenin's and Norton's theorem. In order to derive Thevenin's and Norton's theorem, I have assumed that our circuit is linear, and keeping in mind linear circuit, we have basically taught this whole course. And so this is the story of the first part of the course. In second part of this course, I have started with the AC circuits, and actually due to COVID-19, I am not able to take the physical classes. So I have start doing recording, and after that we have again seen that how to extend whatever result we have talked during the DC network to the AC network. And one of the important thing that comes into picture, that if we will convert time domain into to frequency domain with the help of some kind of complex quantity, then somehow differential equation that is treated as a algebraic equation. And in order to do that, we have learned several transformation, and finally we have talked about the three phase network. So, and in three phase network, what we have observed that whatever instantaneous power, that is constant, and material requirement is also less if we want to supply or deliver the same power. So with this whole discussion, I am going to close the today's class, or finally I am going to close this course. But of course, all lectures are now online available, and I have already talked about the book. So book by Hayat, that is very much fundamental book. So after going through these lectures, please also try to go through the book, and this is one of the most fundamental subject. Based on this subject, in latter part of your semester, you are going to learn about the classical control system. There again, whatever analysis, whatever transfer function, whatever I have defined, same way people are going to derive the lot of they are going to generalize about the system. So their mechanical system, lot of different system will involve, but almost analysis, core part of analysis is remains same like the electrical circuit. And this course is also helpful to understand the power electronics, and lot of course. If you understood this course, then it is possible to think about the development of other courses. Due to that reason also, this course is one of the most fundamental course. So with these remark, I am going to close the today's lecture as well as this course. So thank you very much for your cooperation.